the energy levels is good for us. Why? Because it will allow us to amplify more wavelength. We'll see that now in details. So we have the ground state, the metastable state, and the pumping level. The difference between the ground state, before we go into that. So at equilibrium, the ground state will be more populated than the metastable state. To achieve a population inversion, we will need to increase the population of metastable state. How do we do that? By using a pumping signal at a wavelength of 980 nanometers. Why 980 nanometers? Because this is the wavelength that corresponds to the energy difference between the ground state and the pumping energy level. So what will we do is pump the atoms from the ground state to the pumping level, and if you remember, we said that by spontaneous emission, the atoms will fall down to the metastable state. This process takes a very short time of 1 microsecond. This microsecond is referred to as the spontaneous emission lifetime. So this is the time it will take if we pump an electron, an atom from the ground state to the upper state, to the upper level. It will take only 1 microsecond before it falls down to the metastable state through spontaneous emission. So now we will have higher population in the metastable state, but it will tell me, okay, they will not settle down here. They will also want to go down back to the ground state through spontaneous emission. Yes, that's true, but the spontaneous emission lifetime for this, for the difference between these two levels is much higher than the spontaneous emission lifetime between these two levels. It's 10 microseconds. Okay, so they will stay here for considerably long time. During this time, if there is an incident optical signal with an energy that is equal to the difference between the metastable state and the ground state, what will happen to that signal?
Sorry.
So we agreed that now we have population inversion, and this population inversion will last for 10 microseconds. That's long time. It's during that time we have an incident power signal at an energy that is equivalent to the difference between these two states. What will happen to that signal? According to what we discussed here. We have now population inversion. We have satisfied the condition of population inversion.
Amplified?
Yes,
Yeah,
this will result in amplification because we will have more transitions from here to here that will result in emitting photons or amplification. Okay. What is the energy or what is the wavelength that corresponds to the energy difference between these two energy levels? By a very lucky coincidence, the difference between these two is or not okay. We said there are energy bands, so there are a number of levels here. The difference between these levels corresponds to wavelength in the range of 1525 up to 1570 nanometer. What's special about these numbers? Okay, maybe it's not clear for you what are these numbers. We agreed that the metastable state is not just one level, it's multiple levels. And also the ground state, multiple levels. The difference between these levels, okay, between the different levels, all the different possible combinations, corresponds to wavelength in the range of 1525 to 1570 nanometers. What's special about these numbers?
Was it from the first lecture?
Yes.
Talked about 1.55
Yes.
micro.
And what was that?
That was for the
The range of optical fiber.
no,
Hmm?
it was-
The range which optical fiber working.
The range that optical fiber work.
no, it was where almost.
Yeah, okay, but you need to be more accurate in your description. It's not okay. Optical fiber can work in all the optical spectrum.
It's where we had the shifted
More efficient projection.
Remember, we said we had 3 windows, low loss windows.
0.8, 1.3.
0.8, 13, 10, and 1550.
Yeah.
Okay, so by a very lucky coincidence, this is the low attenuation, low loss window that the fiber works on. Okay, so can you see that this is really lucky and amazing that we have this beautiful coincidence?
Can you imagine?
Wow.
Yes, wow. We should all say wow.
Wow.
Because it's
Same
optical,
problem.
the ECFA is really a major milestone in the development of optical fiber networks. Without it, we will not have the optical core networks we have now. Okay? So, we said we were very lucky that the difference between these two bands corresponds to the low loss window for optical fiber. Okay. The pumping power, the pumping wavelength. If you remember, we just said we can do pumping at 980 nanometer or 1480 nanometer. The 1480 corresponds to the difference between the highest level in E2 and the lowest level in E1. So what we will do here, like we will pump the atoms from the lowest level here to the highest level here. So we'll not use the 980. Okay? And this corresponds to nanometer. However, the 1980 is more efficient. It achieves higher population inversion, okay, which will mean lower noise. We'll talk now about noise. And but the 980, the 1480 nanometer has the advantage that it can propagate or travel through the fiber. The signal can travel through the fiber with minimum loss, because this is very close to the 1550 window. Okay, which means that we can generate this signal, the pumping signal, at a node and send it through the fiber to the amplifier, and this will save us from having active components in the middle of the link. Do you see the advantage here? Because the 1480 is within the range the minimum loss range. It can travel through the fiber from the node up to the middle of the link where we have the amplifier and do the pumping. So we don't have to install the laser pump in the middle of the link. Okay, which is something can be considered inconvenient because of maintenance and so on. Also, the 1480 has a high output power. So the 980 nanometers is used for applications where we want low noise amplifiers, where the 1480 is used for applications where we want a high output power, and also if we want to avoid having active components in the middle of the link. Okay. Spontaneous emission. We said that the atoms will not stay here forever. After 10 seconds, they will go down and emit a photon. But is that photon good for us or bad? We are having more photons, but is it a good photon or a bad photon?
Usually good. Mostly.
Mostly what, good or bad?
Good.
No, it's not good. Remember, when we were describing stimulated emission, we said that the emitted photon will have the same energy and will be coherent with the incident optical power. It will have the same polarization, phase, and propagation and direction. The spontaneous emission, the photon, yes, will have the same energy, same wavelength, but it will be incoherent. It will be, can propagate in any direction, can have any phase, any polarization, which means that it will not add to our signal. This is one thing. The other thing, it will propagate through the system, through the fiber, and the fiber will consider it as an electromagnetic field, and it will just amplify it as it's amplifying our input signal. Which means that the population inversion we have achieved will be used by this spontaneous emission signal instead of our input signal, which might cause the amplifier to saturate. So you can see that it will not add to our amplified signal, our input signal, and it will result in wasting the population inversion we have achieved and causing the amplifier to saturate. So spontaneous emission is a source of noise. We refer to it as amplified spontaneous emission noise, ASE noise. Okay? Any questions?
Excuse me, Doctor.
Yes.
So here, as you mentioned, this is 1550 nanometer, and you mentioned this is not good because it is incoherent. So why do you need to repair it?
What is not good exactly?
This is for the incoherent because maybe there is a different phases or a difference from the situation with them.
Yeah, okay.
Same phases.
Oh, yeah. All what you are saying now is about the spontaneous emission.
Yeah.
Why are you mentioning the 1550?
Because here you told us the photon emission, this is here is not good.
No, I didn't say that. What I said is, let's revise the whole process.
Yeah.
We have more atoms at the ground state. We want to achieve population inversion. We want to take these atoms and put them at the metastable state. How do we do that? by pumping the system with an input, with a signal that will be absorbed by these photons to go up to the pumping level, higher than the metastable level we are targeting. Okay? Because of spontaneous emission, they will not stay there for long. Within 1 microsecond, they will all go to the metastable state. Yes, they will not stay in the metastable state forever, but the spontaneous emission lifetime between these two levels is 10 milliseconds, while it was only 1 microsecond here. So you can see now we have good amount of time that we can do something during that time. During that time, if we have an incident optical signal, it can be, or it will induce transitions from the metastable state to the ground state. So photons or atoms will fall down to the ground state and emit a photon. This photon is what will cause or which will result in amplification. Okay? We talked about spontaneous emission. We said that they will not stay here forever. They will fall down. In this case, they will emit a photon. This photon will still be at the same energy, same wavelength, but it will be incoherent with the incident signal. It will be that can propagate in any direction, can have different polarization, phase, whatever. So it will not contribute to our amplified signal. In addition to that, it will saturate the amplifier because it will use the atoms that we have raised up here, population inversion, to amplify the spontaneous emission signal instead of amplifying the input signal. Okay, which will cause the amplifier to saturate. Yes, Nicholas?
Yeah, but where does the pumping energy come from? Is it like
Laser. This is what we have seen here.
Talking about laser.
Okay.
it's like an external
Yes,
pumping?
yes.
So it's like we got our signal and additionally we got the laser.
Yes, and
and
we talked here about joining them together using a coupler.
Okay.
Okay.
So actually we can use, let's say, 70% of the laser energy to amplify because we pump
70%?
the roughly estimate because we pump it on a higher level to 980 and then it falls down.
From where did you get 70?
No, it's just like if I look at this graphic, we burn some energy because of this little time period where we can save the metastable state.
Okay, continue. I'm not getting your point. What
So-
do you want to say?
So we use a laser, and the
Uh-huh.
laser is pumping the atoms to the pumping level.
To the high level,
to the
yes?
high level. So and then it drops down after 1 microsecond, you said?
Yes.
And this energy difference, this energy difference here is like
Is what we get from the laser.
yeah, okay, but
Yes.
this is like wasted and it's not like that's the amount we lose for amplifying our signal.
Yes, yeah.
Okay.
And so, what was your question? Yeah, what was your
Yeah,
question?
that's fine. Now it's fine.
It's fine.
Yeah, how? Because
So there are two types of emission. Good emission, the stimulated one. The emission stimulated by the incident signal. This will be coherent with the signal. This is our amplification. There is spontaneous emission that happens regardless of the incident power, an incident optical signal, and this will have, yes, the same energy, but it will be incoherent. So it will not contribute to our amplified signal, and it will saturate the amplifier because it will propagate through the amplifier, and the amplifier will deal with it as any electromagnetic field, and it will amplify. So the population inversion we have achieved will be used by this spontaneous emission instead of being used by our original signal. So spontaneous emission is bad for us. It was good when we raised the signal up and then drop down. Up to here, it's good for us. But other emission, a spontaneous emission between the metastable state and the ground state will not be good for us. Okay? And we talked about the two options we have for the pumping. We can pump, I think this is what was confusing you, Maryam. We can pump to the 980 level, a wave, or the difference between the ground and that upper level corresponds to a wavelength of 980 nanometer. Or there is another option of 1480 nanometer, and we talked about the advantages and disadvantages of each. So we talked here about that each level is actually a band of levels. And we said that this is good because it will allow us to amplify a range of wavelengths. Because if it was only a single level, then we will only be able to amplify the wavelength that corresponds to the energy difference between these two levels. Okay, all this frequency or all this wavelength. But when we have multiple of them, then we'll be able to amplify the wavelength that corresponds to the difference between these two, all the combinations we have. So we'll have a range of wavelengths. And this is very good, we said, for the BDF system, wavelength frequency, and we'll discuss that in the next section. So the EDFA has a large bandwidth. Here we can see the EDFA gain profile versus wavelength at a pumping power of 220 milliwatts. And what we can see here that the gain is not equal for the different wavelengths. Why is that? Because initially atoms within these different levels of the energy bands are distributed randomly. They're not distributed equally. Okay, so obviously the level with more atoms will result in more amplification to the wavelength corresponding to the energy between it and the ground state. You see that? So that's why we have this unequal gain. The bandwidth here is 30 nanometer. And we have the peak gain at 1531. This not flat gain causes a problem for us, especially when we have cascaded amplifiers, when we have multiple amplifiers, multiple EDFAs, which means that for one wavelength, or one wavelength will be amplified more than another wavelength. Okay, although here the difference does not look very huge, but when we have cascaded amplifiers, many amplifiers connected, then the difference between them will be significant. And this is a problem for the BDM system. How can this be mitigated? It can be mitigated by using or replacing the silica fiber with fluoride fiber. So now this amplifier is referred to as EDFA, erbium doped fluoride fiber amplifier. F, double F. However, this has its problems in terms of noise because it has to be pumped at the 1480 nanometer. It can't be pumped at the 980. Okay, so sorry.
Always a trade-off.
Yes, as usual. Okay. So let's try now to summarize the advantages of FFET over repeaters or the regenerators. What did we say at the beginning?
Conversion.
Hmm?
There's no need for conversion to F.
Yeah, so we get rid of the optoelectronic conversion. Everything is done in the optical domain. Okay, this is one. What else?
No loss.
Hmm?
No loss.
Yes, low insertion loss splicing. The loss is less than 0.02 dp per splice.
Larger band.
Larger band. Yes. And also the high gain. The gain, as we can see here, can be about 20 or more than 30 dp.
You said something about format. What exactly do you mean the format?
Modulation format.
Modulation format.
The bitrate and modulation format is transparent to modulation format and bitrate. When we upgrade the system, when we want to go for a higher wavelength, higher data rate, we don't have to replace the editors. While for regenerators, we need to replace all the generators each time we replace the system. And for regenerators, we will need a regenerator for each wavelength. While for ETFA, it has a large bandwidth, and as we said, it can amplify multiple wavelengths together. Okay? So where do we use ETFA? We mainly talk now, or we only talk now about using them as inline amplifier to replace the regenerators. Where else can we use them? So we talk now about ETFAs replacing regenerators as inline amplifiers. Okay? Where else can we use them? We can use them as preamplifiers before receivers to improve sensitivity. So before we receive the signal, we amplify it, so the sensitivity would be improved.
And then post amplification. Are they using post amplification as well?
Yes, but what is post amplification? This is at the receiver, after the laser and before the transmission. use is to compensate for losses in switches.
Excuse me. After what?
After laser and before transmission. So at the transmitter, after we generated the optical signal with the laser, we amplify it before we transmit. At the receiver, before receiving the signal, we amplify it, so the sensitivity will be improved. For switch. So to compensate for losses due to splicing, inserting devices or components, and also losses in switches, in optical switches. Any questions? So we talked about the amplified spontaneous emission, and we said it's the source of noise. Actually, it's the main source of noise in it. And we said that the photons generated because of spontaneous emission, they are not, they are incoherent with the incident signal, so that's why they are not, or they do not contribute to the system, to the amplified system. The power spectral density of this amplified spontaneous emission noise is large, and it's given, as you can see here, as where MT is the number of orthogonal polarization states. For a single mode fiber, we have two orthogonal polarization states. So MT will be 2 if we are not using a polarization filter, and it will be 1 if we are using a polarization filter. And then HBV here is the frequency. We're using it as F, the equations in the previous section, but need it to be so don't get confused. H is the Planck constant, G is the gain of the amplifier. Okay? For real amplifiers, it will be even worse, because you will have to consider the amplifier excess noise factor. This is the amplifier, the noise figure we talked about last lecture, or 2 lectures ago. When we talk about it as a ratio, we call it factor. When we express it in dPs, we call it figure. So here it's ratio, so we call it the amplifier excess noise factor. Okay, so this is the power spectral density of the amplified spontaneous emission at the output of the amplifier.
What was again in the execution?
M is the number of orthogonal polarization states. And for the single mode fiber, it will be 2 if we don't employ a polarization filter. It will be 1 if we have a polarization filter. We only allow 1 polarization state. Okay. The output noise in the electrical domain can be shown to be composed of 4 components. So now at the electrical domain, at the receiver, okay, the noise will be made of the shock noise due to the signal power. This is what we have considered so far, in our previous lecture, the shock noise. The dark current and the quantum noise. Okay. We will have also thermal noise. It's not shown here, but you can add it. Thermal noise. Then the noise resulting from the amplified spontaneous emission. The amplified spontaneous emission, similar to the signal, will result in shock noise. Okay? Because it's also a signal received, so it will also result in shock noise. And just to remind you what is shock noise results from the variation resulting from the random arrival of electrons, or the random generation of electrons that will make the detector current. These can have two sources. We said the dark current noise, and this is because of electrons are jumping through the depletion area of the PN junction randomly, and this is what the dark current noise, and the quantum noise due to the random arrival of photons. These together make the shock noise. So the signal itself will have shock noise. The amplified spontaneous emission will also have shock noise. Okay? It will not only result in shock noise, it will also result in beat noise. Then noise signal, the amplified spontaneous emission noise signal, will beat with the signal. Beat means that they will interfere and they will generate another signal at a different frequency. It will also beat with itself, because we said it's incoherent, so it will have different polarization in different phases. So these different polarization, different phases will beat, and they will result in different frequencies. So these are the possible sources of noise. Shock noise due to the amplified spontaneous emission, shock noise due to the beat between amplified spontaneous emission and the signal, and amplified spontaneous emission with itself. This is in addition to the noises resulting from the signal itself, shock noise and thermal noise. Okay? So now this is just based on what we already know. The shock noise due to the amplified spontaneous emission. We have just seen that the current is responsivity multiplied by the power. And responsivity is given as you can see here. This is what we show earlier in the lecture. Q is the electron charge. We used to have this, don't get confused. Okay, and we have just seen that the power spectral density of the amplified spontaneous noise is given as you can see here. And this P, this BO refers to the 0.7 bit rate. We said we will filter the signal to reduce the noise through a filter that has a bandwidth of 0.7 the bit rate. So this is the BO. We are calling it BO, the optical bandwidth, to distinguish it from the electrical bandwidth. This is the bandwidth that we have been talking about when we talked about the front-end design and so on. This is the bandwidth of the receiver. Okay?
So this
Post
will always
detection.
be 0.07.
Huh?
This will always be 0.07.
What?
This one, BO.
No, it's 0.07 of the bit rate.
Okay.
Okay? Remember we called this bit rate earlier. So that's why we are multiplying the spectral power density of the amplified spontaneous emission noise by this optical bandwidth. So if we just substitute the P there, we will have this expression. And this is the amplified spontaneous emission noise, the shot noise due to amplified spontaneous, or the current, the photocurrent due to the amplified spontaneous emission. To get the noise, you remember this? We said the Schottky formula to get the shot noise, 2EIB. So we got the current due to the amplified spontaneous emission. So now we can get the noise, the shot noise due to the amplified spontaneous emission. So we have just taken the formula here. The I we obtained from here and substitute in this formula, and we got this. Finally we end up with this. So we said this is the optical bandwidth. This is the bandwidth of the phi of the filter. Will pass the optical signal through before it goes to the receiver, and BE is the post-detection bandwidth. This is what we have been trying to maximize with the preamplifier, the front end structure design. So yes, so this is the shot noise due to the amplified spontaneous emission.
Excuse me, Doctor. So it will take another maybe substitution, because you know what we talk about coincident is right. And what about BE for substitution?
BE is what we have considered earlier for the structure, the front end structure design. So then what is your question?
This is 0.7 literate.
Yes.
And this is by how much? Because I just know.
Okay, if you want to calculate BE, then we'll give you the total, the RTL and CTL, the total resistance, total capacitance, and then we'll tell you whether it's a low impedance or transimpedance amplifier and so on.
So calculating from the previous equation.
Shot noise due to the signal itself. So again, the Schottky formula, and we have I as the power, incident signal power, PS, we call it here PS for signal, and this is the responsivity. So we just substitute and we end up with this. This direct substitution. So this is the shot noise due to the signal power. Shot noise due to the beat between the signal and the amplified spontaneous emission is given as you can see here. We'll not go into the details of how we obtain it. If you are interested, I can give you books and papers. And also for the beat between the amplified spontaneous emission noise with itself, given as you can see here.
But this equation, is it required from us?
Yes.
All of them?
Yes. Obviously, for these, you can obtain them.
From each other.
Yes, that's fine.
But for the last two.
The last two, as I said, if you want to know how they were obtained, come to me and I'll give you some papers and books. And if not, then memorize them.
But for the exam, we don't need to memorize the formula. We get like a great sheet of formulas.
No.
What?
No, because you know, you asked me this question before, and I said formulas are either they are, for example, the thermal noise. You should know the thermal noise is 4 kTb over RL. That's easy. Okay.
There's only one number.
So no paper, no documents at all at the exam.
No, you will have a list of the constants. Why are you so scared of this
Yeah,
one?
what's the
So
point?
you want the education about
You can always
You
look
never know.
we can always look up the equations when we want them. Test our ability to use them.
As
When to
I said, any other equation is either very simple, or you should know it, like the thermal noise or the Schottky formula. Okay, these are essential. Yes, we didn't go through how they were obtained, but take them as they are. Others, just obtain them. For example, you will not go and memorize that responsivity R is equal to quantum efficiency multiplied by E over HF. You don't have to do that. You know what is responsivity, so you can start from the beginning.
Well, for this one,
Memorize it.
Oh, why it have two HV? Why not cancel each other?
Where?
It's two HV. Yeah.
Ah, you mean this? Okay, sorry, cancel them then.
You can't.
So there's no HV in.
Okay, because I don't know this by heart. Okay, the last thing is the bit error rate. You have seen that the bit error rate is given, as you can see here, the complementary error function of this. And you remember we said that the Gaussian distributions over around A1 and A0 are the same. We assume that they are symmetric. And we assume that because up to that point, all the noise was additive. So it exists whether the signal is there or not. So the signal at 1, or the noise at 1 is equal to the noise at 0. While here, when we look now at the noise due to the amplifier, noise at 1 will be different than the noise at 0. Noise at 1 will be made of all the components we have looked at. The shock due to the amplified spontaneous emission, the shock noise due to the signal itself, and the beat noise between the signal and the spontaneous emission, the spontaneous emission with itself. While for 0, we first have to set the signal to 0, so then this will not be there. Okay? While the shock noise due to the amplified spontaneous emission will always be there. The signal is there or not. Because in the amplifier, even if you are not applying the signal, still the spontaneous emission will exist. And the beat noise between the spontaneous emission and itself. Okay? So having this in mind, we have to go and modify the bit error rate, the argument of the complementary error function, and it will include the variance of the noises at the two cases, at A1 and A0. That's all. We're not going to how we obtain it. important, just to see that now they are different. As we said, the shot noise.
Here, but this sigma 1 and sigma 0. But in the equation is sigma 1 and sigma 2. So sigma 0 is the sigma 2, you mean?
Ah, yes, sorry.
This is sigma 2. Yes.
No, this is 0.
Another
What is sigma 0? Why it's not? Why?
for reading sigma 0, this is for logic 1, and usually activity the same.
Yeah, sure.
So the average is divided by. Another thing, Doctor, in the previous slide, you mentioned addition of the thermal noise.
Yes, I was going to talk about this now again. So, why we didn't include the thermal noise?
Sigma 0.
Earlier, because the components that we have just shown for sigma 1 and sigma 2, which includes the spontaneous emission, shot noise due to spontaneous emission and due to the signal and the bit noise, dominate over the noise of the receiver, which is the thermal noise. So that's why it's considered to be less important. So if you don't mention it, it's not a problem, but if you want to mention it, then this will be good. These are typical values for an amplifier in terms of the spontaneous emission, electrical or the gain, the bandwidth, optical and electrical bandwidth, efficiency and different, the error rate, bit rate, and so on. That's it. Any questions? Yours? Sorry, I took my.
That's fine.
Yeah, can I ask one question? No.
Yes.
Okay. So we ask.